branch points and branch lines. So we are going to see what are branch points and branch lines. So from now on, I'll concentrate only on things that are directly related to a syllabus. And what you have to do is you have to do the small numericals related to topics that has already been done and topics which are familiar to you. So suppose we have a function w is equal to z to the power half. Okay, now let us look at this like this. Suppose this is the z plane, then let's suppose we'll let z to make a complete circuit like this. Suppose it's going this way, like this. It's coming back to this A. So let this point be O and let this point somewhere, this OB is the axis, and it's moving in this direction. So what we do, we allow Z to make a complete circuit in the anti-clockwise direction. Complete circuit in this manner as shown by the arrow sign. So it has started its journey from A, suppose, and let this angle be θ1. So this is θ1, that means theta is equal to θ1. And now Z is equal to r e to the power I theta, as we know it is like this, which is called the polar form, because you see it is nothing but r cos theta plus I r sin theta, which is nothing but, you take the r common, it is e to the power I theta. So we have learned this earlier. So what is W then? W is obviously z to the power half, so it is r e to the power I theta the whole to the power half, which is equal to r root over r and e to the power I theta by 2. So we are looking at a particular type of function w, which is equal to what? W is equal to z to the power half. So for this function, you see, after a complete circuit back to A, suppose after complete circuit back to A, we can write that W is equal to how much? It is root r e to the power I. It was θ1 earlier, so I should have written θ1. I could have written here θ1 like this. It will become how much? I twice pi plus θ1 by 2, which is equal to r e to the power I. This is what? Pi plus θ1 by 2, which is equal to what? Is it not r e to the power minus I θ1 by 2? So you see, it was this much. This is 1, okay? So please don't get confused. This is θ1 by 2 here. It completes a revolution like this, but you see it's not again like this. It now becomes minus of, sorry, this is not minus, this becomes minus of root r because of this 1. So as you know what is exponential, when it is pi by pi plus this, a minus sign comes over here. So we find that it's like this. Thus we have not achieved the same value of w as we come here. So it has not achieved. However, if I make two rotations, then what will happen? After another rotation, that means that is 2 rotations in total. So when you have 2 rotations, then what happens? Then we would have written this plus, so I could have written another minus twice pi plus, so another negative sign would have come up and we would have written it. This would have become what? Root r e to the power I theta 1 by 2, which is the same value as it started here. Or I could also write it like this from the first one itself, that r e to the power I 4 pi plus theta 1 by 2, which would have been root r e to the power I 2 pi plus theta 1 by 2, which would have given me the value root r e to the power I theta 1 by 2. So you see, we arrived, that means after making 1, if this is A, I make 1 complete revolution, I don't get the same value of W. But when I make 2 rotation, then I get the same value of W. So we have to make 2 rotations like this. So we can state this problem in this manner, that if theta is this much, if when theta lies between 0 and twice pi, at the time we are on one branch of the multiple valued function. We had already seen that z to the power half, w is equal to z to the power half, was a multiple valued functions having 2 values. So it had 2 branches. So now we can say that we are on one branch of the multiple valued function z to the power half, and when then theta goes from twice pi to 4 pi, actually this should be like this. So in this we are on the other branch. So for this we get a negative value, and for this we get the positive value of w. You see, we get whatever we get w, the value of w or the value of the function in this part is opposite of in sign to that in this one. So these are said to be 2 branches, and we have this figure, this one we had O and this was B. So we can say that if we consider B to be at infinity, you see that this is one branch and this is another branch. We can say it this way, and this is called the branch line or the branch. This line is called the branch line. Or branch cut also. This is also called the branch cut. This O is called the branch point. This is called the branch point. So this is a rather complex kind of an idea, because the very name suggests we are doing what? We are doing complex variables. So things are bound to be not as simple as functions which are real. Here we are talking about complex, because see, the whole idea of complex number rests on I cap. And what is I cap? I cap is root over -1. So obviously things will be more complex. They will not be of a form that can be imagined by our limited imagination. So you see, things will be very, very abstract here. So I'm sure you'll understand these things about branch point and other things when we start doing a few numericals on branch point and branch lines and all these things. Now limits and continuity and these things are not very different from what we did in our calculus, so I'll not go to these things and I'll directly move on to the Cauchy-Riemann condition, which is very important. That is the next chapter, the third chapter of your book, that is complex differentiation and Cauchy-Riemann equations. They are also called the Cauchy-Riemann conditions also. Now for this we'll remind ourselves of what is a derivative. We know that derivatives for a single valued function fz, its derivative is f dash z, and it is equal to limit delta z tends to 0 f of z plus delta z minus f of z divided by delta z. Students, is this not just the definition of f dash x or y dash? So you see, you are all familiar with these things of this idea or this expression for differentiation. I'll just stop with analytic function. Analytic functions if the derivative of fz, that means if f dash z exists at all points z of a region R. So we have a region R where there are different points, complex variables z, and then if it is analytical everywhere, it is a derivative can be found everywhere, then fz is analytic there. I'll stop here.